All right, so going back one slide here for a second so we can look at this. The equation for a voltage divider is you have your supply voltage times the value of resistor 2 over the sum of resistor 2 plus resistor 1, and that is equal to your output voltage. Now, let's take a look at this in a diagram. Here, resistor 1 is resistor A, resistor 2 is resistor B. So you have the voltage times resistor A over resistor A plus resistor B, and that is going to be your output voltage. That's how to calculate the output voltage. And you can use resistors to get a very specific voltage. So if you're limited to like a power supply that only outputs 5 volts, and you need, let's say, exactly 2.67 volts, you can use resistors to get that voltage exactly what you need. There are certain components that if you apply too much voltage, it'll burn out. So you can use the equation indicated here on the previous slide to figure out exactly how to get your voltage. Now, jumping down, you can actually use several of those environmental dependent variable or resistors as one or more of those. Actually, you typically only use as one of the resistors in that equation, and that's how you create a sensor. Okay, so you'd use a light-dependent resistor, like a photoresistor, as one of those resistors. And if you knew what the range of the resistance was for that resistor, you could then use a voltage supply, a second static resistor, and you would have apply a certain voltage, and then you'd have a very precise output voltage depending on the light levels. So this is how they fabricate sensors, using photoresistors or thermoresistors, or you can use potentiometers or piezoresistors for like pressure plates. There's a lot of different types of materials that'll change their resistance depending on various environmental factors. Now, using an op-amp as a non-inverting amplifier. And this is the diagram where you have a feedback loop going back, where you have your resistor 2. Sometimes they'll be written as resistor sub F, which is a feedback resistor. What this does is this will amplify an input symbol or incoming signal, but it won't invert it. A lot of our inverting amplifiers will actually invert that signal. So when you get an input voltage of, let's say, 2.5 volts positive, it comes out as 2.5 volts negative. Okay, it makes sense when you put this on an oscilloscope. It doesn't make sense just talking about it. You'd actually have to see this on an oscilloscope to make a lot of sense. Now, to calculate the gain of a non-inverting amplifier, you simply take 1 plus the value of the feedback resistor divided by the value of the resistor going to the ground. Okay, the equation is represented right here. Now, to get the output voltage, you'd multiply that gain times the input voltage. Remember, gain in all cases has no unit. Gain is not measured in amps, volts, ohms, anything else. Gain is just a multiplier, so it's unitless. Remember that. Now, if you look at this on an oscilloscope and take a look at the wave for it, the output the output voltage is going to be proportional to the input voltage. That is the difference between voltage 1 or voltage 2 and voltage 1 between A and B. Outside of that range, you're going to get saturation. In other words, the signal is going to flatline at the upper levels, and you're not going to have the signal anymore. So it's very important to have a power supply, to know what your power supply is when you have an input signal, so you don't exceed that power supply. Now, when you use a non-inverting amplifier and you have a gain, you'll notice the signal at the top is your input signal, where you have a fairly low, a fairly small difference between the crest and the trough of the waveform. When it is amplified, the period of the wave doesn't change. That is, the distance between crest and trough and crest doesn't change, but the height, the amplitude rather, of these waves will change. That's what gain does. It just changes that amplitude. Now, assuming a 13-volt power supply, the waveform becomes saturated, and when it gets to that point, it flatlines. We've been talking about saturation a whole bunch of times here. Now, why does that matter? Remember, when you use an op amp that has a gain of 10 to the 8th, you're not going to be limited by the operation amplifier. You're just going to be limited by that power supply. So when it reaches the top of the wave, it won't go any higher. When it reaches the bottom of the wave, it won't go any lower. That's clipping and limiting, collectively known as saturation. Now, calculating the gain of an inverting amplifier is very similar. Here, when you get the gain, you're going to multiply the input voltage to get the output voltage. But to get the gain, you're going to take the negative value of the resistor going back to the non-inverting input, or the inverting input rather, over the value of the other resistor on there, and multiply that times the voltage, and that's how you get the output voltage. So it inverts the wave. So what's that look like? Well, assuming here you have, this is going to look more like what, a sine wave versus a cosine wave, I guess. So it passes through your origin here. Remember here, though, the output is going to be inverted. Okay, inversion. Woo. Now, calculating the gain, or calculating the amplitude, this is actually pretty easy. This diagram, I like this diagram a little bit better because it actually has the voltage numbers on the left side. You'll see, again, it looks like the wave on the right is bigger and it just has higher amplitude, but the period is exactly the same. That's very important to remember when you're calculating these waveforms. Now, also notice that the amplified waveform, which is the one on the left, assuming the gain is 2, the input waveform varies between positive 1 volt and negative 1 volt. The amplified waveform varies between positive 2 volts and negative 2 volts, but it is inverted. Okay, so where there was a crest, there is now a trough. Where there was a trough, there is now a crest. Make sense? That part should make sense. Awesome. Now, how does saturation affect this? Just like before, when the waveform gets to the limits of the voltage supply, then it flatlines. So you'll get waves that look like your typical sine waves or cosine waves, but when it gets to the top or the bottom, it flattens out. So the take home from all of this is know what saturation is. Know what saturation does to a wave. Know what inversion is. Know what inversion does to a wave. And then know how to diagram an operational amplifier. Make sense? You're wobbling your heads, shaking, nodding, kind of a combination of everything. So hopefully we got everything. Awesome.